Hello. Can you all hear me? Good afternoon, everyone. Let me double check the sound. If you can hear me, you just give me a response. Thank you. Okay, good. So okay, double check. I can hear myself. Test. 1 second, 2 seconds, 3 seconds, 4 seconds. Okay, 6 to 7 seconds. So Monday, I have covered about the graph. So from Monday lecture, you should be able to know how to represent the graph. We only introduced two kind of a representation. One is adjacency metric. The other one is the adjacency list. They are pro and con depend on the problem itself. Whether you need to random access to check the adjacency between two nodes, or you just want to know all the adjacency nodes of particular vertex, then you will choose the appropriate representation. And a lot of time, because we do the graph, our objective is at least at this level, I would say at least at this level, the easiest problem we want to work with the graph is a traversal problem. Which means that my problem, I just need to visit every node in the graph once and get whatever information, then I can find out the answer I want. Then in such a case, you may just need a systematic way to visit every node. And should you choose the adjacency metric or adjacency list, you can think about it is in the way like what I mentioned just now. If you choose the adjacency metric, you can random access. You can immediately check that whether the vertex X and vertex Y are adjacency nodes or not. Because it's a V by V metric. It's a V by V metric. You can all the adjacency information are stored in the metric. You can easily randomly access any two vertex, the relationship, whether it's 0 or 1. If it's a weighted, there's a weight or no weight, or infinity or whatever. So from that, you can very fast to get the information. But sometimes you want to check some application, some traversal problem is you want to know all the neighbor. If you want to know all the neighbor, you will find that adjacency list will be better, because adjacency list is a linked list. You want to know all of them. You don't care how many are they, but you just want to access all of them in sequence or in whatever order. That's when you need to check everything. But if you use the adjacency metric, whether they are connected or not connected, you still need to you need to read the whole row. So you will spend a lot of time to read a lot of element item which is not connected, which indicates 0, that they are not connected. Then you will waste a lot of time. Compared to adjacency list, the linked list, you read the next node. If they only have two nodes, means that only two vertex are its neighbor. Then you can very fast. But if you use the adjacency metric, then you need to check all of them, and then you find out that who are that two neighbor. So depend the application. But anyway, back to the today lecture, I will talk about the traversal of graph. Traversal graph, the thing I want to visit, my problem is I need to visit every node in every vertex in a graph. And every vertex only just need to visit once. I already can get the information I want and make some decision. Then I just need a very systematic way to visit every node once. And every node will be visited in the end. So there are two. Here we introduce two. Hopefully I can complete it today. Otherwise, I will carry on Monday. One is the breadth first search, the other one is the depth first search strategy. And then, so first I will talk about the breadth first search traversal. It's very similar, or I would say that actually they are the same algorithm as the level order traversal of the tree, which I think we have covered in the first half in the one of the tutorial question. Where's my cursor? Yeah. So that means level order traversal or breadth first search is like you trying to visit. The idea is like level by level. That means let's say I start from you definitely need to indicate where is the, for the graph, not like a tree. Tree we know that there's a root, but for graph there's no particular nodes considered as a root, generally speaking. Yeah, for here, let's say I trying to use this as an example. I start from the nodes 11 as a starting point. I need to indicate it first. Otherwise, there's in the graph there's no one can claim itself as a root. Yeah, no such concept in the graph, generally speaking. So I myself need to define one of them. Let's say I start from 11. So breadth first search is a level order traversal. So that means after you visit the 11, the next one you trying to visit is these two, 1 and 2, because this one is just, the distance is just one edge only. So these two will be the next one. Then so-called breadth first search is the next one will be after 1 and 2, the next level will be 4, 3, 6, and 5. Then the level order after this should be 8, 7, 10, 9, and 10. Then the last one will be 12. So that one is like a systematic way to expose the edge. Yeah, directly connect to the vertex before you move further. So you will be level by level to visit all the nodes systematically. That is the breadth first search strategy. So that's when you visit the 11. The next one is 1 or 2. So here you need to take notes that for the breadth first search, you can see from here, first I need to tell you where is the starting point in the graph, not like the tree. Binary tree, of course, you very intuitive. You definitely start from the root, but from the graph, I can start from any one of them. There's no right or wrong. It depends on the problem itself. So I need to provide some information. Where is the starting point? Where is the source? So here I let 11 as a source. Second thing you need to take notes is the next one you need to visit is 1 or 2. I said 1 or 2 means that the order in the breadth first search algorithm itself, they didn't say you should visit 1 first or you should visit the 2 first. Yeah. So usually we also need to provide the information about the visiting order. When you have 2 nodes or more nodes in the same order, like in this example or this example, 4, 3, 6, 5, you need to have some definition, provide some additional definition about the order. Otherwise, everyone will come out different result. So let's say I trying to set in the ascending order. That's when you find that when you visit the 11, you realize that 11 have 2 neighbors, which is unvisited, 1 and 2. You will visit in ascending order, so you will visit the 1 first, followed by the 2. In such case, then you will visit 1 first. After you visit 1, you realize that there's a 4 and 3 behind. Then 4 and 3, you will choose visit 3 first, followed by 4. After you visit 2. Because you must visit 1 and 2. After 1, you must visit 2. Then before you move on to the next level. So that is so-called the breadth first search. Okay? So next level will be 8, 7, 9, or 10. Then last one will be 12. So that is the breadth first search. So how do we achieve such a breadth first search algorithm, traversal algorithm? If you observe just now, actually you already learned in the first half lah. You will find that I visit 11. After 11, I know that only after you visit that particular nodes, you will realize that this particular nodes has how many neighbor. Whether you use adjacency metric or adjacency list doesn't matter. But only after you visit it, you will go and check. Then you realize that it got 2 neighbor. So you must visit these 2 neighbor first. That's so-called breadth first search. So the nearer one you will visit first. So 1 and 2 you must complete the visiting. Then you can move on to the next level, which is 3, 4, 5, 6. 3, 4, 5, 6. If I visit in the ascending order. Then if that is the things, you should realize that actually I need a queue to help me to queue out the order. When I visit this guy, I know that I will put 1 and 2 in the queue. Then when I visit 1, I realize that there's a 3 and 4. I need to put them in the queue. But 3 and 4 I must visit after 2. Then after you visit 2, you realize that there's a 5 and 6. Then you will visit 3, 4, 5, 6. After you visit 3, you realize that there's a 7 and 8 after 3. Then you must visit 3, 4, 5, 6. Then followed by 7 and 8. Then follow. That means that I need a queue to let me first in, first out, to sort out their visiting order. So not surprising that I need a queue structure to assist me. So to achieve this, let's say I use another example here. This graph, this is a directed graph, also can. It's a directed graph. Then I got A, B, C, D, E, F, G I need to visit. So I need to use a queue. And my starting point, as I mentioned, I need to provide a nodes as a starting or the source nodes. So after I visit the A, I should find out that A, the adjacent is B is 1, C is another one, then followed by another one is F. I'll visit in alphabetical order. So that means you need a queue. First I enqueue A first. Then I dequeue A at the beginning. Then I dequeue A. Then A considered as visited nodes. After you visit the A, you realize that there's a B, C, F, 3 nodes. Then let us enqueue them in alphabetical order. Then I will put the B, C, and F into my queue. Then in my loop, I will repeat that I will dequeue the B. After I dequeue the B, I will enqueue whatever haven't into the queue. So C will not be selected because C already in the queue. So I need some marker or something like that to indicate that this particular thing is already in the queue. Otherwise, you will repeated visit the same nodes again. So that means that this one I only concern is I need to add the D into it. But D only can be visit after C and F. So after C and F. So the next one I will dequeue is the C. So I will visit the C. So when you visit C, you will realize that C, there's no any path. I cannot go to anywhere else except because it's all towards C. There's no outward arrow signs. So C, you only can simply visit it, no more neighbor. So you can just visit the C. Then after C is F. I will dequeue F. F has 2 neighbors, which is A and C. However, both of them already visited. So after you visit F, after you're trying to visit F, you also won't enqueue anyone. Then the next one, you will visit the D. D will be the last one. After you visit D, you will find that D can go to C and A, but C and A already visited, so you won't revisit them. Then you will stop. So that there's a circumsystem like this one, you will find that in this circumsystem, showing you that from A, there's no way for you to reach the E and G. If you start from A, you won't be able to reach E and G. There's no path. So in other words, this particular graph also show you that they are not strongly connected. It's not a strongly connected graph. This particular graph, through the breadth-first search, you can realize that it's not a strongly connected graph. So that is also one of the applications. We can use the breadth-first search to check whether the graph is strongly connected, the directed graph is strongly connected or not strongly connected. So this is the algorithm. Yeah, as I mentioned, I wouldn't provide the code for you because I want you to try to implement by your own. After you get the idea, yeah, you should know that you need to create a queue to assist you. Every time you just need to enqueue the vertex into the queue, and then after you enqueue into the queue, you will mark it as visited. Then you will start with a while loop. Every iteration, you will dequeue one of them and enqueue all its neighbor, unvisited neighbor, unvisited vertex adjacent to it, to W. All the adjacent unvisited vertex adjacent to the nodes itself, and mark it as visited and enqueue it, mark it as visited and enqueue it. Just like earlier you see when you put the first one, when I put the dequeue the A have BCF, I will enqueue BCF. The question is like BCF, you need to take notes that is in alphabetical order or reverse alphabetical order, or in what kind of order, because in the breadth-first search algorithm, they didn't set you must B first or C first. There's no particular rule saying so. Depend on the problem. So you need to see whether what is the condition we tell you, or the problem need. Sometimes maybe we didn't directly tell you. It can be due to like the problem you want to solve that problem. You must sort it in particular order. You must visit in particular order. Then you can solve the problem. Then you should implement in that manner. Okay. So that is the things. So you keep doing this. When the queue is empty, it doesn't mean, another thing is from earlier example already show you, it doesn't mean that it's not like a binary tree. When the queue is empty, it also doesn't mean that you already visit all the nodes. You may, for directed graph, you may not. For directed graph, you may end out that you can see that there are two nodes you cannot reach. So there are two nodes is unvisited. Even the queue is empty. You already visit all the nodes you can reach, but doesn't mean all the nodes in the graph is visited. It can be some nodes, unfortunately, you won't be able to reach there from A, in this example, from A. But you may be able to, if you start from, I think if you start from E or you start from G in this example, yeah, you should be able to reach other nodes, any other nodes. If you start from E or G. But if you start from A, you start from B, you start from D, C, F, this, yeah, if you start off, yeah, these few nodes, then you won't be able to reach the E and G in the end. So from this algorithm, yeah, we can extend a lot of problem to, yeah, you can use it to solve a lot of this kind of issue, whether the nodes is strongly connected, directed graph is strongly connected or not strongly connected, you can determine. Another thing you can learn from it is also can find out the path. You can find out the path from A from A to any reachable vertex. Like from here, you can see in green color, I can find that from A to D, from A to D, the shorter path is from A to B, B to D. This is also can use the breadth search to tell me there's a path from here. Yeah, there's path from A to F, or there's a path from A to C. Yeah, the shorter path from A to C is this one and not this one. Yeah, so you can find the shorter path from vertex A to vertex, any other vertex. You also can find whether they are connected or not connected. So if a vertex has several unmarked neighbor, then you need to take note that by the algorithm itself, breadth search didn't set you have to visit which one first. Theoretically they have equally correct to visit them in any order. So you need to read the question. Definitely we will provide some additional information to you. Otherwise everyone will come out different solution or different output. Yeah. And then second thing, from using the breadth search, I can find the shorter path from particular vertex S to any vertex V. I can find out all the shorter path from the source to any vertex. Yeah, because you use this kind breadth search or level order. So you will use the minimum number of edges to form the path to that vertex if it is reachable from S. Yeah, if it is reachable from S, you should be able to use the breadth search to find out the path. Then if the tree you form, the tree built by breadth search is known as just a name, breadth spanning tree. What does this thing means? Back to here. So here you see that this green color one, it form a tree after that, showing the path is A to B, then A to B, then after that there's one to be the F, then there's another one is the C. For this particular problem, the spanning tree should be looked like this. D. Yep. So this particular spanning tree is known as breadth search spanning tree. Yeah, that is what it means, the breadth spanning tree. And from the spanning tree, you also can learn their distance. You also can learn their connectivity, whether it's a strongly connected or not strongly connected. Then you may not enough. Sorry, strongly connected or not strongly connected, you need to try all of them. You cannot just use one node to conclude. You need to try all the nodes. Just like you can see in this, just now this example. If today I start from E and G, then in the spanning tree, all the nodes will include in the spanning tree. But if I choose A as a starting point, then you will find that E and G, I won't be able to find them in the spanning tree. So you need to try all the nodes as a starting point. Then you can make a conclusion whether they are strongly connected or not. I think that one I will ask you to do it in, I think it's in the lab. Yeah, I will release it soon, probably tonight or tomorrow. So application, yeah, I would say there are just this simple algorithm can have a few possible application. Yeah, you can check whether the graph is, they are connected component. You can learn to understand the connected component by using this algorithm. You also can check all the vertex within one, whether it's within one connected component or not, and so on and so forth. You find the shorter path, between two vertex. Today I want to travel between two locations. If that, for unweighted, for unweighted graph, right now I'm talking about unweighted graph, I also can use the breadth first search to find out where the shorter path between two vertex. I just choose one of them as a starting point, and then I keep visit. I don't have to form the complete spanning tree. Once I visit the other nodes, I can stop already because I already found the path. Okay, so that is the breadth first search. For the time complexity, so you can find that each edge is processed once in the while loop. For total cost is in OE. Then every vertex you need to visit once, so so it will be in OV. Then total depend how you implement. Actually, you will find that it depend how you implement, because every time I visit the nodes, I visit one node, I need to check the neighbor. So I need to know all the neighbor. So like if you use the like I mentioned at the beginning, if you use the adjacency list, that means that whole linked list tell me all the neighbor immediately. I don't need to check whether they are neighbor or not neighbor. Who are my neighbor? I can immediately know the adjacency nodes. And all these nodes in the linked list, in the corresponding linked list, I will enqueue them directly and mark them as visited. Then next iteration, my queue will dequeue each of them and then carry on. But if you use the adjacency metric, it's different story. Adjacency metric is a V by V. That's it. I need to read the whole row, that particular row, to find out that all the neighbor. Then I need to scan all its neighbor. Then it's already take me V, big theta V times. Then I need to do this V times, because let's say it's fully connected. The worst case is all are connected. So that's mean I need to check V square. The total times the worst times I need to take V square. But for this one, if I use the adjacency list, is V plus E. So if your graph is a complete graph, then no different. If your graph is a complete graph, then there's no different. But if your graph is a very sparse graph, that means sparse means that a lot of zero, they are not connected, they're not fully connected, maybe very sparse, something like this. Then you will find that I only give you 5 nodes. Imagine that you got 500,000 nodes. Then you will find that this one will be much more efficient than this one. If it's complete graph, then actually no different, because when they are a complete graph, this one, the number of edge will be V squared. V times V minus 1 will be V times V minus 1 divided by 2. So overall is still V squared. So then whether you use adjacency list or adjacency metric, the computational times, the time complexity in the worst case are about the same. Okay. So that is the time complexity of breadth first search. Okay, I still have another 20 minutes. So probably I can try to complete the depth first search. Then next week I can start with a new topic and start release the next assignment 5 soon. So depth first search, again, this one you also have learned it in the binary, for the binary tree. The idea is very similar. So it's very similar. You can refer back to what you have learned in binary, the pre-order traversal of binary tree. So that first search, the idea is there is a kind of a greedy strategy. It's a kind of a greedy strategy. I'm trying to expose the path as far as I can, as deeply as I can. I'm trying to move as far as I can. Until I cannot find any nodes further, Then I reverse back one step back and check any alternate path. So same thing, you can see this example here. The same example, now if I use the depth first search, what does it mean? If I start from 11, same thing, I start from 11. I try to a greedy strategy. As long as I see there's a variable nodes, I will try to visit. So since I see one is a variable, is my adjacent nodes, I will I don't check the rest. I don't check whether still got other neighbor or not. Like breakfast is check all the neighbor. This one you just check as long as there's one unvisited vertex as your adjacency nodes, then you will trying to use it. You will trying to visit there. You will go to one. And after you visit one, you will find that one have another 3, 2, 3, 4. You can choose any one of them. Then you try 4. Let's say I try 4. And after 4, no more. Then 4 no more, right? So you expect that after they visit this guy from here to here, then 4 no more, then they will reverse back. They will back, so-called backtracking. They will back one step back. Then they will try another path, which is try the 3. Then after they try the 3, 3 got another one, I think I choose 7. Then 7 have no more, then I reverse back. Then I will try 8. Then 8, then I try 8, have another one, which is 12. Then 12 no more. No more other, there's no any unvisited vertex nearby. Then I will backtracking to 8. 8 also have no more already. Then backtracking to 3. Then 3 also has no more, no other. Then backward to 1. 1 still have one more. 2 have not visited yet. Then they will go to 2. Then 2 have another 2, 5 and 6. So I try the 5 first, followed by 6. 5, then reverse, then go to 6. Then after 6, you will visit, I think I choose 9. Then reverse, backtracking. I should use backtrack, they call backtracking. Then try the 10. Then after that, no more, right? Then backtracking to 6. Backtrack to 2. 2 backtrack, no more, all are visited. Backtrack to 1. Then backtrack to 11, back to the initial nodes. Then that means that you already visit all the nodes by depth first search. That is the depth first search. Excuse me. Okay, so that is the depth first search, the idea behind. So same thing, you have learned in the pre-order. You can expect that this thing, to implement it, there are 2 ways. Or yeah, you either you use a recursive approach or you introduce a stack, because you need to visit every time is a last in first out. Whenever you find there's one node, you will visit first. Then later you cannot go further, then you will backtrack, then to visit the earlier unvisited nodes vertex. So that means you will store, which means that if I want to achieve such thing systematically, that means reverse. So starting from 11, 1 and 2, then I need to have a stack to put 1. I think I will put 2 first and then 1 first, 1 letter. Then you push it, then you pop 1 out. You pop 1 out. So 2 will be at the bottom. Then after that, this one is already, then you will try 4, 3 and 4. Then you will put it into the list which is not visited. Then you will push 4. Any unvisited nodes, 3 and 4, you will put into the list. Then you will keep doing this. Yeah, I think I put 4, so I need to put 3 first. The order is not important. If purely talking about depth first search, but for particular application, it become very important. Yeah. So here just illustrate. So the order, I think I didn't follow any order. Yeah. by right I need to indicate is ascending order or descending order. Yeah. So I keep doing this. By using the stack, I can visit all the nodes in the end. And you can see that just now the pattern is like you're trying to visit as far as you can for a certain path. If this path cannot work, then you backtrack one level and then check whether then you will pop up another new nodes and trying to go through that path. Maybe I can show same directed graph. Same thing, you also work in directed graph or undirected graph. Yeah, I need to use a stack to help me to achieve this depth first search. So let's say we start from A again. Then when you visit A, you can choose B, C, F. So I choose after I visit the A, then you visit the B first. Then after you visit the B, then B can go to C or D. Then you choose to visit C. Then after you visit C, then you can visit the D. After you visit C, no more. C, same thing. You know that C, there's no more path for you to move further. Then you will backtrack. You will back to B. Then B, there's another one, which is D, which is unvisited. Then you are trying to visit D. As long as there's any nodes is unvisited, you will visit first. That's a strategy for depth first search. The depth first search, later I will talk about the application. So after that, you try to visit D. D does not have any. Yeah, A is already visited. C also visited. Then this guy have no any new unvisited. There's no any neighbor is unvisited. Then you will backtrack. You will backtrack to B. Then B itself also have no more unvisited vertex. Then he will backtrack to A. Then after you backtrack to A still have one more, which is F. Then he will visit F. Then after you visit the F, not surprising that you will backtrack to A and you have no more other reachable unvisited nodes because E and H is not reachable from A. So implied that from here, as long as I can find one example, from A you are not reachable to H, E, and E, then I can conclude that it is not strongly connected. But if you want to prove the directed graph is strongly connected, you need to start from all the vertex and try once and confirm that in all any vertex can reach any other vertex. There's a path for you to reach any other vertex. For all the nodes you need to try. Yeah. So as long as you find one, then you can conclude it's not. But you want to prove it's strongly connected, then you need to try all of them. That probably is one of the application already. So in short, you can expect that this one, instead of you need a queue, breadth first search you need a queue, depth first search you need a stack, just like pre-order traversal in the binaries tree. So you need you create a stack, then you're trying to push the vertex into the stack and mark it as visited. Then not surprising, the stack at the beginning you won't be empty. You just push one guy into it. So I will pick it to check what is the value and denote let's say denote it as W. Then I will check whether it has any unvisited nodes adjacent to the W. And then after that, if there is, then I will if there's no, then I will pop it. I will pop this particular guy. Yeah, no more already. This one is no more. Okay, you can pop it. Otherwise, I will push that unvisited adjacent nodes into the stack and then push and push and push and push and mark it as visited until I can't find any. So if you're doing that, you will find that eventually all the reachable vertex will be visit once. Yeah, this is one of the algorithm for depth first search. Yeah, you can think, not surprising. I think it's same as the pre-order. There's another version. I think it's put in the lab also. Yeah, it's instead of using stack, you also can, just like the pre-order traversal in the binary tree, you also can use the recursive function to achieve it. Here I show you is the iterative approach. Yeah, you can think about it. I think I will show in the lab if I'm not wrong. Lab or tutorial? I think should be the lab. Yep. Okay. Maybe okay. I still have some time. Maybe I can demo this idea in earlier example. Okay, let's try this algorithm. You can refer that, but just now that slide for this example, reverse. Okay, let's have a stack, follow the algorithm. I create a stack. Then first I put the 11 into the stack. I push it, so the stack is not empty. So while as long as the stack is not, when do you use, there's no, as long, actually it doesn't matter as long as you can solve the problem. It doesn't matter you use an iterative or recursive approach. As I mentioned, I think if those attend the first half tutorial, yeah, you can see that whether all the, generally speaking, I can set that all the stack, all the recursive function is possible to convert it to equivalent iterative version, because when you do the recursive one, is implicitly you let the computer create a stack memory for you to store the status for each recursive call, and then you can last in first out. So not surprising that if you want to convert a recursive version to iterative version, you need to introduce a stack data structure to store some information, just trying to mimic the recursive version. So they are equivalent. Normally they are equivalent. Yeah, I would say normally they are equivalent. The advantage and disadvantage I can see is like, because recursive one, every recursive call, they are somehow independent. Because when you call another guy, then all the variable you create, later you return back, sometimes you not easy to find back the things. If you, okay, this one later, I will demo it again. Let me explain Jeff Lin question. If you notice just now, yeah, here don't have example. Maybe I use the example show you. You can see if you have the stack, there's an advantage, because you can see let's say I start from 11, now I push the 11 then the next one, there's among the 11, I pick it according to the algorithm. I pick 11. Okay, 11 have two neighbor, 1 and 2. So it's a greedy strategy. I just push one of them first. I push 1. Okay, 1 is unvisited, mark it as visited. So 1 is visited, I mark it as visited. Then I look at 1. 1 got 4, 3, 2. Then I select 4. I push 4 into it and mark it as visited. Then 4 have no more unvisited neighbor. Then you pop it out. So first, you can see that before I pop out, recursive function, if you have a recursive version, you already return. But if you use the iterative approach, you look at the stack. The stack tell you something. Yeah, 11 want to reach 4 is 4, 1, 11. There's a path from 4, 1, 11. But if you use the recursive function, recursive approach, yeah, you may not be that easy to find out this particular path. Or it's still possible, but just like you need, not that convenient, that easy. Just read the stack, you can get the answer already. Because it's a recursive. The stack or the stack memory is implicitly in the program. You're not easy to access them. But this one is explicitly I create. Then I can very easy to access them. So that is, if you ask me, yeah, when do you need to use iterative or recursive? Then if I need to know the path for all the possible path, then I probably will use the iterative one, because easier to implement to get the answer I want. Okay, so I carry on. So this one no longer useful, no more unvisited nodes around. Then I pop it out. I carry on from 1. Then 1 I will check 3. There's 3 and 2. Then greedy strategy. As long as I can find 1, I will put it first. So I put 3 into, I push it 3 into the stack. Then 3, I carry on 3 with 7, 8. There's a 7 and 8 greedy strategy. Then just like whenever as long as there's 1, I just push. I think I push 7. Then 7 no more. Then pop up 7. Then try 8. 8. Then 8. Then there's another one, 12. Then 12 no more. So when I pop up, when I start pop up, it's called backtrack. Pop up 12, I backtrack. Pop up 12, I will back to 8. 8 have no more. Then pop up 8, backtrack to 3. Then pop up 3, you backtrack to 1. Then 1 still have one more, which is 2. Then you carry on from 2. Then 2 have 5 and 6, you try 5. Then 5 has no more, then you pop up and then backtrack to 2. And keep doing this. Then 6. Okay, I don't want to continue. Then 6, then 5, 9, and then 10. Then after that, you will backtrack, then you pop up. Then when your stack is empty, that's in you already visit all the nodes which is reachable. For directed graph, of course, as long as they are not as long as it's not open, there's no as long as there's an edge, they're reachable. For directed graph, yeah, then it may be end up like what this one you can see. This one, yeah. In the end, A is not reachable to E and H. From here, you also can find out. Okay, so that is the depth first search. So same thing. If a vertex has several neighbors, you need to know the order. Or the question itself, somehow they need to tell you the order. Maybe sometimes I maybe tell you explicitly is alphabetical order, in ascending order, in descending order, in whatever kind of order. Sometimes the problem, you want to solve that problem, you must visit in particular order. You need to observe whether what is the right order. Then that will become, that means I won't explicitly tell you the order. You need to figure out by your own. Then that can make the question very difficult. So if the graph is strongly connected, then there's a tree constructed by the depth first search algorithm in a spanning tree, including all the nodes, a set of vertex, and also that one also can provide you the path to visit the nodes. If the nodes is not inside, that means from A, in this example is like from A is not reachable to E because E is not inside. So this particular spanning tree is also known as depth first search tree. Okay. Yeah, so just now the E and H is not reachable. But if excluding E and H, this particular graph is considered strongly connected. If you only have A, B, C, F, D, I think all are reachable. No, this one also not strongly connected, because C is not reachable. So I also need to excluding C. Okay, so answer the other guy's question. Application, these are all a lot of application for depth first search. Typically is like checking the connectivity. Of course, you can use it. finding the whether there's the connectivity, all these are connectivity, articulation point, the cut vertex of the graph also can, whether they are open or not. Another one, real world example, is solving some puzzle. You want to find whether, like, solving some maze. If you have a maze, you can form a graph of the whole maze, the grid, and then you're trying to check whether you can find a path or not. Yeah, you can use the depth first search algorithm. I think you will be better than the breadth first search because it's a greedy strategy. If I can go along this path, I will try to go along this path. Only when I cannot go the maze through this path, I will backtrack and then try another path, and then try another path, and then backtrack. This path cannot, and then I backtrack, and then eventually I find the exit. If I cannot find the exit in the end, that means this is a failure maze. There's no path for me from the entry to the exit. And sometimes we also can use the depth first search to analyze the topology sorting. Is like example is like your cost. So today you can reach here is because you passed the 1003. So because it's a prerequisite, then under this there's a 1007. After 1007, there's another path is to 21. Yeah, our program is relatively simple. So this one, and what database, I can't remember the code. Database, all this. So you can use the depth first search to also find out the cost, the prerequisites, all the prerequisites code from 1000 module to 2000 module to 3000 module to 4000 module. Yeah, if you want to pass this, you want to reach taking this particular module, what is the prerequisites module you need to clear first? Yeah, so maybe that also is another example for depth first search. Okay. Yeah. So okay, maybe I end the last two slides for today's lecture. So again, same thing. The graph representation will affect your time complexity. So use depth first search, breadth first search. You only visit each node once. That's what you want to do. Yeah. Then every edge is travel forward and backtrack. So you expect that you only do, yeah, each edge worst is only visit twice only, forward and reverse forward and backward. Yeah, backtrack. So they're known as backtracking. So using the adjacency list, then the time complexity, you need to visit all the nodes once, and then the worst is all the edges you will use it and visit it. So worst is V plus E if you're using the adjacency list. If you use the adjacency metric, not surprising that every time you want to check all the neighbor, you need to read V. Yeah, remember that every time in this algorithm, I think is, yeah, although this one is a if-else statement, in the implementation is not just simply if-else statement. Yeah, I need to check whether any nodes is unvisited. That means I need to read the whole row. Then I can judge whether any unvisited vertex is around. So that one may not be, although here the pseudo code, I wrote it as a if-else statement, but in the actual implementation, you may not be able to simply use the if-else statement to achieve it. But adjacency list, it's a linked list. So if this node is, yeah, you just simply check the linked list. But if it's adjacency metric, then you need to check the whole row again and again and again and again in every iteration. Then it will become V square. So that is the things. So in this lecture, I just introduce you to I would say quite simple algorithm for graph traversal. So one is a breadth first search, the other one is depth first search. Generally speaking, breadth first search is using queue to achieve it. Then depth first search need to use the stack to assist you. Then the complexity wise, one is if you use the adjacency list, then is the V plus E. For these two cases, for these two search algorithm. Yeah, if you're using the adjacency matrix, then the complexity will go to V square. So the graph I will release soon. Maybe, I don't know, should I release it tonight? Or maybe, yeah, I still see a lot of people have not logged into your assignment 4. Please log in it and start doing it as soon as possible. Yeah, because the invitation link is only can last for 2 weeks, but the assignment got 15 days. So if you're trying to log in the very last day, just start trying to do the assignment, you may not be able to log in. I probably would not resend the invitation link to those people because the last minute is not possible. You can complete the assignment, and what is your intention is very obvious. So rather than let your friends get 0 marks, I better don't send you the invitation link. Okay, any other question? When the tutorial, when everyone attend after the end, so I think the last section should be on Friday. So I better release the solution, the tutorial and the lab solution in after Friday to be fair. Otherwise, Friday section people will be unfair to them. Okay, so after either Friday or Saturday, I will release the answer. Remind me if you didn't see the answer in the NTU Learn for tutorial and lab. Yeah, assignment I will not release the solution. Anything? If not, I will end the section. Thank you for your attending. Goodbye. Okay.